All right, welcome to example 3 on lesson number 1 in unit 1, net external forces. In this third example question, we are going to be solving a problem here. It's similar to question 2, except this problem is going to be in 2 dimensions. And by that I mean there's going to be both x and y forces being applied here. Now, if we look at the diagram, in fact, normally in the process of solving this question, I'm going to break it up into steps because it's quite a long solve. But we have forces pulling at angles here. So we have what looks like 40 degrees north of east. We can draw on our little compass here if we want to. We can do northeast, southwest. And so this angle's pulling, or this force is pulling up at an angle 40 degrees north of east. Similarly, here we have another angle pulling the opposite, well, not opposite direction, but to the left and up, as opposed to the right and up, pulling at 30 degrees north of west. Okay, perfect. Now I mentioned I was going to break this problem up into 4 parts because it is a little bit of a long solve. So while you're solving this on your sheet, I'd recommend writing a little bit smaller. It's tough to fit the space sometimes. All right. Now the 4 steps to solving these problems, if they're 2-dimensional, number 1, I would say always draw yourself a diagram. This example happens to have one drawn already, but it's pretty dicey if you don't draw yourself a diagram. So draw a diagram. What's different in dynamics, or what's different when drawing free body diagrams from drawing the diagrams back in the displacement unit, is I generally recommend drawing your free body diagram all with your forces pulling out of some central object box. It's kind of the convention for the style question, and if you were to draw these lines tip to tail, it would lead to a resultant line, and you could solve it that way. It's just not really the way that we typically will do it. So we'll leave it at that for now, and we'll break into the steps to solving this. So similar to when we were doing displacement problems that are all paths taken at different angles. So we have the classic, we're going for a walk style question. So we can say, we walk east. So this question, maybe I'll use these values. So we walk like 40 degrees north of east, 500 newtons. So we draw our first arrow like that. And our second arrow for force 2 is, up to the left, something like that. And our last one is straight down. All right. Well, just drawing this, we can see that our resultant is going to be something like this. Maybe, it's tough to say. Maybe this line's longer, so maybe it will be like that. So maybe our resultant line's like that. I'm probably not making any sense here. But really what I want to say is similar to back in displacement, we are going to want to create or figure out all of our x values, all of our y values, and then we're going to redraw a triangle with the net values. I'm getting a little ahead of myself. So let's just do step 2. Step 2, actually I don't even need to label it step 2. I'm just going to put a 2 and circle it. And we're going to call this solve net x. Okay, and we did this back in displacement. So on our diagram, we only have 2 arrows that have any x values. Force 1 is up and to the right. Force 2 is up and to the left. So they both have x values. We have to solve for those. Those x values, maybe I'll do in red here. And this is going to be coming out to here. Oops, I need to lighten that off. This is going to come out to here. This is going to come out to here. If we want to label those, we can call this one force, it doesn't shine very well. Force 1x, that's this one. And this one we can label force 2x. All right. Now how do we solve those? We have a magnitude of force along our hypotenuse, and we have an angle here. So this is hypotenuse and adjacent side, so we can do a cosine. So let's do, oh gee, how do we do force 1 here? Force 1x is equal to the cosine of 40 degrees which is equal to this adjacent side, so f1x over 500 newtons. All right, so if we were to rearrange this now, we could say that f1x is equal to 500 newtons times the cos of 40. And we can solve that. For f1x, I end up with 383 newtons. When we want to add direction to that, that is out to the right. Okay, the direction will be quite important very soon, so make sure you keep track of directions. Okay, let's do f2x. Underline that because it's important. f2x, basically the same math. It's going to equal cos of 30 degrees is f2x over 700 newtons. f2x 700, I'm not going to be doing all of this for the y's. 700 newtons cos 30 works out to negative, I'm going to put positive, 606 newtons to the left. Okay. I'm also not keeping track of enough sig digs here. These values should be a little bit longer. If I were doing this and I had my calculator on screen, I would be storing all these values. So maybe don't do as I do, but do as I explain when doing this yourself, because if you're not keeping, or if you're rounding these off early, you're going to get some truncation issues. So make sure you store all the decimals and only round on the last step. Okay. With that said, we now have our f1x, our f2x. Now what we can do is we can use that fnet formula that we've been using in the past, right? And we can say that the fnet of x is equal to, that's equal to just force 1x plus force 2x, all our x forces. And we can say that's equal to, well, here is where we have to come up with our convention for this question. I'm going to use what I would say is typically standard convention and say that in the x direction, going to the right is going to be positive, and that going to the left is going to be negative. While I'm at it, I'm also going to do my north-south convention. North, typically, positive. South, negative. Okay. So now we have our values to add in. Force 1x, so positive 383 newtons. And we're going to add on our second value, but hold on, this value is to the left. So left, we're going to say it's like going backwards. So this is going to be a negative value. So I'm going to say minus 606 newtons. Really what we're doing here is we are still adding, but this is like adding negative 606, which is like subtraction. It is subtraction. Okay. My net x value, I get negative 223 newtons, which is 223 newtons left, right? So, well, we'll just keep it as negative for now. We know negative is going to the left. Okay, that's the very important value for this first step. Next, I'm sure you've guessed it, you may be working ahead already. We need to do our ynet value. And our ynet value is going to be slightly longer, a little bit more work, except I'm going to show less work because all this trig is taking up a lot of space and video time, but we want to solve the y components of these. So I want this arrow, and I guess that's not very accurate to where it is, this arrow here. And we want to get this arrow here. All right, we're getting a little cramped in here, but this one we can call F1y. This one we can call F2y. All right, force 3, well, force 3 is F3y. It's all y. So force 3 is just F3y. I don't even know if we really have to label that one on here. Okay. My step 3, which, we could turn this into a 3-step problem and we can just call it solve x and y, but I'll say 3, and we can call this solve net y. Okay, back to green. A little darker. Oh boy, okay. I'm going to speed this up. F1y is equal to, that's this one here. It's now going to be a sine value because it's opposite. So this is going to be 500 sine 40 degrees. And if you do the math, plug that all into your calculator, I get 321 point... Oh boy, I can't read my writing. 321.4, I believe, is what that says. It may be a 9. 321.4 newtons. And that's up. Okay, F2y is equal to, again, opposite side over here on the 700 Newton one. So it's going to be 700 sine of 30 degrees is equal to, this one's easy because sine 30 is 0.5. So this one is just 350 newtons up. All right. Our third y value is F3. We can call that, I guess, F3y if we want to. And it's all in the y direction. It's down. So we can call this 1100 newtons down, which we're going to turn into a negative when we add these up. So we can say F net y is equal to F1y plus F2y. All right, this takes a little while to get written out, but there we go. And then we can add in values. So F1y is 321.4 newtons. Up is our positive direction, so I keep it up. Plus another up value, 350 newtons. And now our last one is down, so we're going to say plus minus 1100 or just minus 1100 newtons. So when we plug that into our calculator, force net y is equal to get negative 428.6 newtons. Negative 428.6 newtons. Okay, that is our y net value. That's the end of step 3. You can imagine we're getting pretty close to the end now. I'm going to do this bit in blue, lighter blue, something like that. Okay, nets are solved, x is solved, y is solved. We get to draw a tip-to-tail diagram of our resultant vectors. Here's my line tool. We have negative 223 newtons in the x direction. Negative x direction is to the left. Then we have to add this on to the left. Negative 223 newtons to the left. Or we can just say, since the arrow's pointed to the left, this is 223 newtons. All right. We could then add on our y value, negative 428.6 newtons from the tip. So we're going to add our line down here, like so. And we can label that 428.6 newtons. The last thing we have to do is solve our resultant line. Whoa, didn't have line tool on there. So it's going left and down, so our result line should be left and down. Last stage is solve our unknown side and solve for the angle. Unknown side we can use Pythagoras for, so a squared plus b squared is equal to c squared. So c is equal to the square root of 223 squared plus 428.6 squared. So c, our unknown side length, works out to 483 newtons. And my angle works out to the inverse tan of 428 over 223. I actually drew my triangle in my workbook opposite. I actually drew it down and over. So I actually ended up solving this angle down here. But either or is fine. You can do across and down or down and over. You're just going to have the complementary angle inside. So I'll do a little bit of mental math, and I think I can leap through that one. So we're going to have theta is equal to the inverse tan of 428.6 over 223. So theta is equal to, I get 27.5 south of west, so that will be 62.5, I believe, 62.5 degrees south of west. So you could have also ended up with 27.5 degrees west of south. Either are fine answers. So our final answer, I'm just going to write it all out here then. This resultant line is 483 newtons at 62.5 degrees south of west. That's the end. Now I have a couple things I want to add on here before I let you go. My step 4, I didn't label. Step 4, I would typically say, is going to be draw the resultant triangle. So for draw resultant triangle and solve. Okay, that's that. Common mistakes in these questions. Number 1 is people, if there's opposing directions, especially the left and rights like this, they're going to add them together. And so you're going to get somebody who gets the 383 plus the 606, and they're going to have, rather than ending up with 223 to the left, they're just going to have like 900 and whatever that would be, 989 newtons. And they won't know what to do with that value. It'll be the wrong direction. It'll be too big. So that's one mistake. Second mistake is sometimes people will forget about this net resultant triangle, right? They solve the beginning, they'll solve the x net, they'll solve the y net, and then they'll just kind of leave their question at that and say the person went to the left and down. This last triangle is the solving. This is the setup to the question. All this x and y stuff. This is the finisher. This is where the money's made. So Practice drawing these resultant triangles. Remember, you're only doing these in the 2D questions. The 1D questions are just going to be left or right, or up and down. There's no over and down, which makes the triangles obsolete for the 1D style question. This question is 2D, requires the triangle to be drawn. Okay, I think that's all I have to say. I'll leave it at that. This video is quite long already, but these questions do take a good while to solve. So, see ya.